Good morning, calculus students. How are you doing? We are doing section 3.6 on curve sketching. Curve sketching is not actually on the AP exam, but important components of it are on the exam. Again, you may say, where does section 3.5 go? We already did that because it's on limits with chapter 1. So curve sketching is where we actually take these functions and actually draw them ourselves. And again, you're not asked to do that on the AP exam, but important components of curve sketching are on the AP exam, meaning they ask you, where is a graph increasing in concave up, increasing in concave down, or any combination of that. Where is an inflection point in relationship to max and mins, right? So they'll relate the first derivative and the second derivative often, but the only place in your book kind of where that happens is with particle movement and in curve sketching. So that's why you'll see you only have 4 problems in this section to practice bringing the first derivative and the second derivative together. So how do we sketch a graph? We first collect our vital function data without really needing any calculus. What's the domain? Are there any vertical asymptotes? Are there X and Y intercepts? And can we find them if possible? So what I mean by that is there could absolutely be X and Y intercepts, but you don't algebraically have a good way of finding that. What do you do then? They will show up anyway when your function is increasing or decreasing between max and mins. And if it goes through the X or Y axis, it will show up on its own, but we find them if we can. And and the end behavior, is it a polynomial where the ends are both going up, down, or opposite? Or is there a horizontal asymptote like in B here? Then we collect our first derivative data. Where is the function increasing, decreasing? Where are there max and mins? And then we collect second derivative information. Where is the graph concave up, concave down? Where are there any inflection points? And then we bring it all together and sketch it. So what we do then is we have a chart, but it brings the first derivative and the second derivative together. Here's our intervals broken up by domain issues and critical points of the first derivative and second derivative. So we make our chart after we take the first and second derivative, okay? Test values in those intervals. And then what we do, we have one row for the first derivative, right? We find its sign and then whether it's increasing or decreasing. And then for the second derivative, its sign and then whether it's concave up or concave down. And the reason why I don't have 2 rows for the first derivative and second derivative it gets kind of long. So it's kind of nice to condense it a little bit. And then at the bottom, we put our max and our mins and our inflection points. And we should find that everything comes together really nicely. So let's start. I'm just going to move the camera a little bit. I made a work area over here. We're going to graph this cubic function on our own. And then we will graph this rational function on our own. I just realized I want to move a light that I had it moved before. There, I think that looks a little bit better. And I'm going to move this just a little bit so you can see the work area. There we go. Okay, so let's first go ahead and collect any function information that we can for f of x equals x cubed over 3 minus 9x. Okay, let's see if you can see that fairly well. Okay, let's see. So first of all, it is a polynomial, right? And so its domain is from -infinity to infinity, right? So I have to graph all the way across the graph. Let's see, vertical asymptotes, none. That would be where a denominator is 0. That's not happening. X and Y intercepts, I always do the y-intercept first because that's where x equals 0. And when I put a 0 in, I get a 0 out. So notice that is both an x and a y-intercept. I'm going to go ahead and just record that point right now. And an x-intercept occurs where the y equals 0. Let's see if we can go ahead and find that. See if we're missing any. All right, I'm going to go through and multiply everything by 3, right, to get rid of this denominator. And I'm going to go ahead and, okay, here's where my x equals 0 again. Here, this is going to be, the square root of 27. So that's going to be, right, so this is going to be x equals plus or minus the square root of 27, which is somewhere around, let's see, 5 point something. And again, this is just a sketch. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So a little past 5 and a little to the left of 5 point, like about 5.2. Okay, again, it's okay just to be, it's just a sketch. Let's see, end behavior, because this is cubic and it is positive, that means it's going to be increasing as you go left to right. So it starts decreasing. It starts out, it's decreasing on the left and increasing on the right. So I'm just going to remember, I put arrows there to help myself with that. Okay, I'm going to erase a little bit. Let's get our first derivative data. All right, so let's get that first derivative. The first derivative would be, I'll bring the 3 out front and multiply it. That cancels out the 3 and we get an x squared minus 9. So the critical points here, this is quadratic, undefined. It's defined everywhere. Where is it equal to 0? That's at plus or minus 3. So I'm going to circle that. I'm going to break my, chart up, right, with a -3 and a +3. Let's get our second derivative data. That would be 2x. There we go. Critical points, undefined, defined everywhere. Where is it equal to 0? At 0. Okay, so let's break our chart up then. And I'm going to erase a little bit because it looks like I'm going to have 4 intervals. Right, but I had the original chart just to show you what a typical chart looks like. Okay, so here we go. Here's our intervals. We are going to go from -infinity to -3. Then from -3 to 0. Then from 0 to 3. Wasn't that straight? And from 3 to infinity. All right, let's take a look at this. Test values. How about -4? How about -2, 2, and 4? Right, get a little symmetry going there. Okay, let's get our first derivative going here. Right, so let's look at the first derivative function. That's right here. Let's see, when I put in a -4, this will be positive and increasing. A -2 will be negative and decreasing. A +2, negative and decreasing. And a 4 will be positive and increasing. There we go. Let's look at the second derivative, right? Because you have a function and a first derivative and a second derivative going on, it's a good idea to circle what you're looking at. Okay, so our second derivative, we are right here right now. Okay, let's do our test values. When we put in a -4, this is negative, so it's concave down. When I put in a -2, negative concave down. When I put in a 2 and a 4, positive concave up, positive concave up. Okay, let's look for our maximums and our minimums. Let's see. So here at where a critical point of -3, notice that this is a maximum because the first derivative changes from positive to negative. That's a max, and that is at -3, and we will find the x value that goes with that. For at 0, right, the first derivative does not change sign, so no max or min, but the second derivative does. So this is an IP located at 0. We already know it's actually at 0 because we plotted that point. So, and then let's see, at 3 then, the first derivative changes from negative to positive. We know that that's a minimum at 3. Okay, let's fill in the y values with those maximums and minimums. So let's see, when I put in a -3, here, that's a -27 divided by 3, right? That's a -9, and then plus 27, right? So that is 18. Wow, that's way up there. Okay. Okay, and of course, when I put in a 3, that's 27 divided by 3 is 9. And then that's minus 27, right? And so that's a -18. So that's way down there. There we go. Okay, so let's go ahead and graph. Let's see, we already have our IP right here. I'll list that. Let's put our max on. So we're just going to have to make 18 way up here and -18 way down there. Okay, so the maximum is at -3 and 18. That's a max. And then that was, oops, sorry about that. Did I get that? Yep. And then a minimum was 3 and -18. Just going to mark that as a minimum. Now, when I do the intervals through the points, right, I have a lot of information here. Everything that you see should make sense. Let's do it going through different points. So let's take a look here. I first have to draw the graph so that it's increasing but concave down as I go left to right. And this makes sense because it started down, so it has to go up and be increasing to get to this max. How is it doing that? Concave down. There we go. Let me make that a little darker. There we go. So it makes sense that it's increasing because it has to go through these points as you go left to right. Now let's go to the next interval from -3 to 0. It is decreasing and concave down. This makes sense because it has to hit this point here, right? So it must be decreasing. How is it doing that? Concave down. For the interval from 0 to 3, it is decreasing but concave up. That makes sense. It has to get down to this minimum point here. So it must be decreasing. It's doing that by being concave up. And our last interval from 3 to 0 is increasing and concave up. And again, it makes sense that it's increasing because it has to go through this point and it has to continue upward, right? And so how is it doing that? Concave up. And in general, it makes sense because we know what a cubic looks like. Okay, I'm going to erase and then we will do this next rational expression, right? Needed a little something different. You do have polynomials and you do have rational expressions to graph in this section. So you'll be graphing 3 problems and just interpreting on your last problem in 3.6. Okay, so let's go ahead, get a new chart going. Okay, let me get a new graph going here. Okay. All right, so we're working on B here. So here is the function. F of x equals 2x squared minus 2 all over x squared plus 3. All right, let's go through our function data here. The domain, negative infinity to infinity. My eyes go right here. Is there an x that can make this denominator 0? No, there's not, right? Because this would have to be a -3 under my hand. And when you square something, it cannot be negative. So it's from negative infinity to infinity. There we go. X and Y intercepts, let's give it a try, right? So my Y intercept is where X is 0. And when I put a 0 in, let's see, I get a -2/3 out. So there's our y-intercept is a -2/3. So I put that right there. Where's our x-intercept? That's where y equals 0, where the function equals 0. And what makes this function 0 is when the numerator is 0. And that happens at plus and minus 1, right here. And so that would be, that's our x-intercept. So 1, 0 and -1, 0. I'll go ahead and record those. Very good. Let's see. N behavior. This is a rational expression. And when I compare the degree of the numerator and denominator, they are equal. It is squared. So the N behavior is a horizontal asymptote located at the division of the leading coefficients, so at 2. So on the ends of this graph, it should flatten out to a value of 2. How do I show that? Here's 2 on my graph. I am going to just show on the ends these arrows showing that I have to flatten out to 2. I don't make it go all the way across the graph. Okay, let's go on to our first derivative data. I'm going to leave myself some room here. All right, let's take the first derivative. It might be a little messy, right, because we have a quotient. Let's see, and I'm not sure I've left myself enough room. I may have to write a little small, but certainly you know how to do the quotient rule, okay? So the derivative of the numerator would be 4x times the denominator minus, I'm going to keep my numerator and take the derivative of the denominator all over the denominator squared. Okay, I'm just going to check my work really quick here because there's a lot going on and we don't need to make a mistake. So the first derivative, I'm just going to clean up that numerator. Let's see. This would be a 4x cubed right here plus 12x. This is going to be a minus 4x cubed. And this is a -4 plus 4x. And this was a 12x here. Let me just check again. That's 4x cubed plus 12x. This would be a minus 4x cubed and plus 4x. Okay, I think I have it. All over the denominator squared. One last time. The first derivative then is the 4x cubes cancel, and I have 16x over x squared plus 3. There we go. Let's get the critical points. The critical points undefined. We already saw this was defined everywhere because we cannot make the denominator 0. Where is this equal to 0? At 0, right here where the numerator is 0, okay? That was a lot going on. I'm going to erase my work for the first derivative and write it up here and then move on to the second derivative, okay? So here we go. If I had a bigger work area, that would be great, but that's okay. So my first derivative is 16x over x squared plus 3 squared. And I found a critical point at x equals 0. And I'm going to circle that. Okay, let's go on to the second derivative by taking the derivative of the first derivative. I'm going to do that down here. Okay, so I'm going to talk my way through the quotient rule. The derivative of the numerator is 16 times the denominator minus, I'm going to keep my numerator and multiply it by the derivative of the denominator. This is going to be a chain rule. I'm first going to take the derivative of anything squared, which is 2 times anything, plus the derivative of the inside function is 2x, all over the denominator squared. So it's now to the 4th power. But I just want you to see that there is a base of x squared plus 3 in each of the terms. And so I'm going to cancel one base of x squared plus 3 here, one here, and one here. Okay, let's clean up the second derivative. So the second derivative then is, let's see, this is 16x squared plus 48 minus, let's see, this is 2 times 2, so 4 times 16 is 64x squared, all over x squared plus 3 cubed. Okay, notice then what I have is I can combine like terms. 16x squared minus 64x squared is a minus 48x squared. Hope you don't mind if I do this to save some room. There we go. And the critical points we will do right here. Critical points, undefined, defined everywhere. Where is this equal to 0? Boy, talk about being at the bottom, huh? That's a square there. That would be at plus or minus 1. Right here, right? If I put a 1 in, I get a 0. If I put a negative 1 in, I get a 0. So that was a lot going on. But we have critical points of 0, positive 1, and negative 1. So let's go ahead. We're going to have 4 intervals again. So it's kind of nice. Our derivatives took us quite a bit, but that's okay. At least we knew what we were doing. You can see now why I just give you 3 sketches to do and one problem, one sketch that's already there for you to decipher. Okay, we're going from negative infinity to negative 1. We are going from negative 1 to 0. We are going from 0 to 1. And we are going from 1 to infinity. All right, broke it up into our critical points. Test values, -2, -1/2, 1/2, and 2. All right, let's check that first derivative. For the first derivative, notice you don't even have to look at the denominator because it's always positive. So we just want to know what that numerator is doing. So when you put in a negative into the numerator, you're going to get a negative out. And when you put a positive into the denominator, you're going to get a positive out. Let's look at the second derivative right here. Again, noting that the denominator is always positive, right? So we're only concerned about the numerator again. Let's take a look. Okay, when you put in a -2 here, the numerator is going to be negative. So this is concave down. When you put a -1/2 here, that's going to be a 1/4, and the numerator is going to end up being positive. So concave up. When you put in a 1/2, same scenario. The numerator is going to be positive and concave up. And when you put a 2 into the numerator is going to be negative and concave down. Okay, let's get our points. At the critical point of -1, no max or min, but there is an inflection point at -1. Okay, at a critical point of 0, decreasing to increasing, this is a minimum at 0. And we already have that point as -2/3. Okay, at 1, no max or min, but there is an inflection point at 1. Okay, let's get the y part of those inflection points. Here's the original function. When I put a 1, I'm going to put a 1 in. When I put a 1 in, we get a 0 out. Oh, I guess we knew that. Don't we already have points recorded at -1 and 1? There we go. So we actually already have the inflection points anyway. Okay, now when we graph this in purple, let's see if this makes sense. Okay, so notice as I go left to right, my graph, because this x-intercept is underneath, it must go up towards this horizontal asymptote. So as I go left to right, it must be decreasing and then continue decreasing and then must increase up into this line. Let's see if this makes sense. Let's look from the interval from -infinity to -1, right? It says that it is decreasing and concave down. Let's do that. Decreasing and concave down. Totally makes sense on where my points are located. Let's look in between -1 and 0. Between -1 and 0, it is decreasing but concave up. Totally makes sense. Notice that created an inflection point here in a minimum, right? Now we should be increasing between 0 and 1. We are increasing and concave up. There we go. And last, we should still be increasing because we got to get up towards that horizontal asymptote. And it is, it's increasing and concave down. Here we go. Notice in creating an inflection point right at that x-intercept. There we go. Look at that. We were able to graph that on our own. I know that took a lot. That's why you only have 4 problems. Have a wonderful day.